So today we're going to learn the integration technique, integration by parts. When we did the U substitution technique, this was a way to undo the chain rule. Now, integration by parts is a way to undo the product rule of derivatives. So let's take two functions. We have a function u of x and function v of x. So these are both functions of x. And I'm going to take the derivative of their product. Because remember, integration by parts is undoing the product rule. So it makes sense that I need to start with the product rule. So let's take the product rule of this. The product rule says I take the derivative of, to get the derivative of the product, I do the first times the derivative of the second. And then I do plus the second, which is the v function, times the derivative of the first. Okay? And so what is that in terms of x? Since I take the derivative with respect to x, this is u times dv dx plus v times du dx. Okay? So now what I'm going to do is I'm going to take this derivative of the product, which is equal to this right here. I'm going to just copy and paste this so I don't have to rewrite it. And I'm going to integrate both sides. So I'm going to integrate both sides with respect to x. Okay. And so when I integrate this with respect to x, these dx's cancel each other in a way. And I'm left with the integral of u dv plus v du. Okay? And then the integral of the derivative is just uv. And now I'm going to use properties of integration where the sum, the integral of the sum is the sum of the integrals. So this is equal to the integral of u dv plus the integral of v du. And so now for the final step, I'm going to subtract the integral of v du from both sides. And I end up with the integration by parts formula, abbreviated IBP, which is the integral of u dv equals u times v. I can get a v out. And then minus the integral of v du. Okay? So this is the formula you need to be walking away with. Now, you use this method when you see a product, so a product of two functions, where one is easy to take the derivative of and the other one is easy to integrate. So one is easy to take the derivative of and the other is easy to integrate. If you can find those two things, then this is the idea you're using whenever you use integration by parts. So use this method when you see product. Okay, remember integration by parts undoes the product rule, so it makes sense that you're seeing some product of two different things. Okay, so when you see a product where one is easy to take the derivative and the other is easy, okay, easy relatively speaking, to integrate. Okay. So how do we pick? How do we pick our U's? How do we pick our DV's? That's the question, right? So how to pick U? Okay, how do we pick the U? And then we'll talk about how to pick the DV. So how do we pick u? So number one, multiple derivatives make it go away. All right. So what do I mean by this? By multiple derivatives making it go away? Maybe if I saw some function and it had like a x cubed in it. So if I made that my u, then whenever I take the derivative of x cubed, I get 3x squared. I take the derivative of 3x squared, I get, well, 3 times 2, that's 6x. I take the derivative of 6x, I get 6, and I take the derivative of 6, I get 0. So eventually that thing goes away. That's what I mean by you take derivatives, multiple derivatives, and it goes away. All right? Another good option for making your u is you can't integrate it. So you can't integrate. Remember, with your u, you're taking derivatives, and with your dv's, you're integrating. Well, if you can't integrate it, then by golly, it's going to have to be the u, the one you're taking the derivative, right? So you can't integrate it, then that's going to be your u. Third, multiple derivatives cycle back to the original. Now, what do I mean by this? That'd be a scenario like if I have sine of x. If I take a derivative, I get cosine of x. If I take the derivative of that, I get negative sine of x. So it cycles back. Maybe it differs by some constant. For this here, the constant differing goes from positive to negative. Okay, so you're cycling back through some constant multiple. Not always exactly the same, but if you kept taking derivatives, you'd eventually get back to sine x, right? So if you wanted to do that, you could. But it doesn't have to go back to the exact same thing. It could be a constant multiple. All right? Now, that's how to pick u, okay? Picking dv, okay? Picking dv, so this is what we want to integrate, right? So we're derivative for u's, integrating for dv's. Number one, by golly, it's easy to integrate. Easy to integrate. So it fits integration rules. So like a good dv, maybe it's like e to the x, right? So that's easy to integrate. Integral of e to the x is e to the x. Okay, maybe a dv is like secant squared x, right? So easy to integrate. Secant squared x is tangent x. Okay, so something that's easy to integrate. It fits derivative rules. So integration rules. Okay. If it doesn't fit it exactly, maybe you can use a u substitution to get it to fit, right? It doesn't have to be the simplest. An easy u sub might help you out to get the answer. Like if it was the integral like 1 over x plus 1, right? So this is really close to ln x, right, plus c, but instead of x, it's x plus 1. Using a u sub will get you that answer, okay? All right, number 2, you pick this dv. If it won't go away by taking derivatives. So what do I mean by this? Well, I mean, we just talked about ln x, so like if you tried to make this, u equal ln x, well, what happens when I take the derivative of ln x? I get 1 over x. What happens when I take the derivative of 1 over x? I get like negative 1 over x squared. Take the derivative of that, I get like 2 over x cubed. and then 6 or negative 6 over x to the fourth. And it just keeps getting worse and worse and worse, right? So that hopefully I did those derivatives correctly, check my math on it. How would you take the derivative of 1 over x? Well, what I would do is I would convert this to x to the negative 1 and then use the power rule. So power rule says bring the exponent out front and then subtract 1 from the exponent. And so, yeah, that's negative 1 over x squared. And you can just play that game to keep getting the next and the next and the next after that, right? So the problem is the more derivatives that we take, the more ugly, the more complicated, right? The more complicated this thing is getting. So that doesn't really help us out. So maybe that would be a good dv. Okay, instead of taking a derivative, maybe we integrate, right? All right, so that's kind of how, I think about finding u's and v's. One thing that the book did that I thought was kind of interesting, they have a little mnemonic here, okay? And so what they say is they use determined to pick the u is this late, all right, late, however you want to say it, right? And so the L stands for logarithmic, okay? So if you see a logarithm, that's definitely a good thing to pick for u, okay? I stands for inverse trig. A stands for algebraic, meaning like x squared or whatever. T for trig, and E for exponential. So if the integrand contains both a logarithmic and an algebraic, well, what do I know? The L for logarithmic comes before the A of algebraic. So what I'm going to do, I'm going to be letting u be the logarithmic term, okay? Because we go by the order late, okay? So the mnemonic late kind of gives me an idea of what might be a good u. So if maybe I had like x squared ln x. I'm not saying this is integrable. I'm just giving you an example here. So if I was using this liate here, right, the logarithmic L is first, so a good choice to see first would be to pick u to be ln x, and then that leaves dv to be, well, what's left? If I picked ln x, well, only thing left is x squared dx, right? Okay. So if I take the derivative of this, du is 1 over x, okay? And dv is going to turn integrated into v, gets me, well, it gives me x cubed over 3, right? And so then I can combine and run through my formula. Okay, so how would the formula work here? This is kind of a capstone going on here. Remember, my formula for integrating is integral u dv equals uv minus integral v du, right? Okay, so what did I call u? So u here is x squared. I'm sorry. U here is ln x, okay? So everywhere I see a u, I'm going to put an ln x. So that's an ln x. And my dv, what is my dv? My dv is x squared dx. dv is x squared dx, so this is x squared dx, okay? So this and this, those are the same things, right? And then this is equal to u times v. Well, what is u? U is ln x times v. What is v? This is x cubed over 3, okay? Minus the integral of v du minus the integral, what is v? V is x cubed over 3. What is du? Du is equal to 1 over x dx. So this is 1 over x dx. Now this part right here, I'm going to rewrite x cubed over 3 first times ln x. And I need to simplify here. I have 3 x's in the numerator and 1 x in the denominator, so that cancels. So I have 1 x in the numerator, or 2 x's in the numerator, and then my 3 in the denominator, dx. And this is easy to integrate. I'm going to pull out the 1/3. So I've got that negative 1/3 out front. And I need to integrate x squared, which is x cubed over 3. Okay. Plus c. And so now that technically that 1/3 goes to that c, but guess what? The c consumes that 1/3, so we can just write c there. So what is my final answer? X cubed over 3 times ln x minus, and then 1/3 and 1/3 make 1/9, x cubed plus c. Okay? And voila, there's my answer. All right? So kind of an impromptu, didn't really mean to work through that, but it just so happened that we did. Worked out just fine. But the idea here is you're trying to pick a u. Okay, you're trying to pick a u if you want to use this liate, all right? L logarithms first, I inverse trig, A algebraic expression, T trigonometry, so like sine, cosine, tangent, cotangent, whatever, and then E exponential would be like your last resort U, okay? So just another option for you, if that helps you out, okay?